My name is Brian Green. This is the introduction to our course, which is Linux Network Security, or I like to call it open source system software security. System software being that category of software like the operating system, utilities, and even certain daemons and services that we'll talk about. But a lot of these open source pieces of software that we rely on in modern IT infrastructure, we're going to talk about some of the security concerns with those and how we can mitigate those risks. And that's mostly what this course is about, and also using Linux as a network security tool. So let's get started. In this unit, this is an overview of the topics for the course. So I'm going to talk a little bit kind of in broad strokes about Linux, for example. So we'll talk about the origins of Linux, where it came from, how we use it, etc. I'm also going to talk about open source software security considerations, things to think about with open source software, how it compares to commercial. We'll also look at the difference between different operating system environments that runs on top of Linux. So basically, we're going to look at distributions, right? Linux distributions. And then we'll also talk about some of the specific security concerns we have around Linux and how we're going to address those in this course. I'll talk about some of the tools we have around network security within Linux. So let's get started. First, let's look at the timeline for Linux. This course is about Linux, so I think it's important for us to have some background in Linux. I'm sure that a lot of you probably have seen something similar in other courses, right? So pretty much every Unix or Linux course you'll take, almost always they start with some background in history in Linux, and this one's no different. So I'm going to give you my take on the background and the history. Starting all the way back in 1946, and it's important for us to remember that, you know, when the ENIAC was created in 1946, which is a long time ago, right? Just at the tail end of World War II, those computers were purpose-built, right? Now, what was important about the computer in 1940, the ENIAC in 1946, what set it apart from all other computers was that it was programmable, right? So prior to 1946, machines were purpose-built to do a specific task. And the task that they were built to perform was only tasks that they could do for their lifetime. What ENIAC changed in all that is that for the first time, a machine was built that could be programmed to do different things. Now, that's arguable the first time. Charles Babbage built a series of machines back in the 1800s that arguably he designed one that could have been programmed had it ever been built, but it was never built. So I would say the ENIAC was the first real, well, as we would describe it today in modern terms, computer. Of course, they weren't called computers back then. Actually, those women that you see in the picture were what were called computers. So the women were actually the computers that programmed those machines. And of course, that term has been used now today to describe the machines that actually do this work, right? So it's a programmable machine, essentially. And that's really what starts all this. And fast forward to the 1950s, we start to see these computing systems that are very difficult to program in the sense that they're not purpose built, right? They're programmable, but they are the software that you write for these computers has to be written for a specific computer. It's machine level programming, right? So you're writing software to run on a specific machine. Well, so what that means is if you bought a computer from IBM and you wrote a program to run on that IBM, on a certain model IBM computer, and then you went out and you got a digital systems computer and you wrote a program to run on digital systems, you could not run those programs on another vendor's systems without making wholesale changes to the program. So you can imagine that really binds your software development to a specific platform. And there's a lot of challenges that come along with that. So what happened was by 1964, General Electric, in cooperation with Bell Labs, with MIT, lending some support, in Cambridge, Massachusetts, they built the world's first, arguably, the world's first multi-user operating system. And that's what they really set out to do, is build a multi-user operating system. But also that very concept of operating system was relatively new. So the idea that you had some layer of software that abstracted applications from the system itself, from the low-level system, from the hardware, right? So this really first opened up the concept of having some abstraction layer that you could put between application software and the hardware that could, for which you can write programs that could run on different platforms. That's a really important concept here, is that this is the first time it was really conceived of the possibility of being able to write portable applications. Portable meaning they could be run on a multitude of different platforms, different hardware, and even different vendors. And this was groundbreaking at the time. So again, and I put the GE logo on there, shameless plug, because I work for General Electric. But there was a couple different companies that were involved at that time. Now, by 1969, Bell Labs had pulled out of that project. Multics, for all of its groundbreaking possibilities, it was a buggy system. It was not perfect. It was used well into the 1970s, the late 1970s. I think it was purchased by Hewlett-Packard for a time and used on some of their mainframe systems, but it didn't really have legs, right? It didn't last all the way into the future, but it did set the groundwork for Bell Labs. Some of the engineers that worked on that project went over to Bell Labs in New Jersey, and they developed what later would become Unix, right? So they developed the first operating system that would later evolve into Unix. And again, it was developed at Bell Labs. What's interesting about Bell Labs is that at the time in 1969, as most of you know, Bell Labs was a telephone company. And they weren't just a telephone company. A telephone company in 1969 was regulated, right? They were given a monopoly. The Bell Telephone Company was the only telephone company in most markets. And the government granted them the right to operate at a monopoly under certain restrictions. And one of those restrictions is that they were not allowed to operate in certain industries, and one of those was computer hardware and software. So Bell Labs, now why did Bell Labs, if they can't operate in the computer software world, why would they develop an operating system? Well, the answer is because at the time in 1969, they were converting the entire telephone system over to computers, right? And this was a huge change for Bell, and it was also something that would save Bell a tremendous amount of money, right? Think about all those telephone operators that they would no longer need if the system was mostly computerized. So for a variety of reasons, it was in their best interest to really push forward the computing industry, and that's what they did. And so in 1969, they came up with, their engineers came up with this idea of making a Multics clone, which they later called Unix. Now, why didn't Bell Labs sell it? Again, Bell Labs was regulated. They couldn't sell it. So that's really where we get this crazy diagram from, right? So Bell Labs creates the PDP-7 operating system, which later becomes Unix. And I've got the dates on here too, down the right-hand side. So this, really starts in 1969 at the top, but the first date I show is 1986. This came from Wikipedia, by the way, so you can go find this. If you go to Wikipedia and look up Unix, you'll see this diagram in a little bit different form. I kind of dotted it a little bit, but take a look at all the different branches, right? So we start with Unix, and Unix branches off into a couple different versions. And if you look at all the pink is all closed source, meaning it's commercial software. And then the green is open source, right? And FreeBSD being the most famous, right? Which was really derived. You follow the lines, FreeBSD really kind of shoots off of the original Unix by 1986, right? So PDP-7 comes out, and later on, Unix kind of branches off to BSD. And then BSD branches into Sun OS. It branches off into some of these other ones you see, Mac OS, by the way, right? So if you're using a Mac, it's really BSD. That's where it traces its origins. Interestingly, if you look on there, the line that comes off of Unix version 7, right, somewhere around 1987, that line goes over to something called Xenix in 1989. Xenix was actually a Microsoft-owned operating system. So Microsoft, in 1986 and 89, they were in the Unix business, right? They had a Unix-based operating system that they sold for business. So Microsoft was kind of the desktop operating system. Their server-based operating system was Xenix. It wasn't a network type operating system, right? Not like modern Linux is today or Unix, but it really, what's interesting is with these lines going all over the place, you see a lot of cross-pollination of things in the Unix operating system. Even to this day, if you go, into AIX, for example, you'll see some code in AIX that really kind of came from Xenix, from Microsoft, right? So Microsoft actually had a hand in all of this, even though we talk about, you know, Windows versus Unix. And likewise, you can imagine that if Microsoft was in the business of, you know, developing software based on the Unix platform, there's a lot of influence in Microsoft Windows from Unix, right? So there's a lot of things, you know, little things in Windows that you'll see sometimes that you say, yeah, it kind of reminds me of Unix, right? Or that makes me think of a Unix POSIX-like operating system. So it's kind of interesting how all this stuff plays together. But, you know, where does Linux come into all this, right? We're just talking about Unix here. Unix is not the same as Linux, right? They're very different. Well, not very different. They're very similar, I guess I should say, but they are not directly related, right? So where did that come from? Well, fast forward to 1987 and 1991. In 1987, Minix is created. This is a Unix clone, right? So somebody basically set out to create a clone of Unix that worked exactly like Unix, had all the same commands as Unix. The same applications that you run on Unix would be able to run on Minix. And that's a really important concept here, right? The idea was that you could take a Unix application and you could run it on a Minix-based application, right? So that was kind of interesting. And then Linus Torvalds, of course, famously in 1991, releases the first Linux kernel, which would later become the Linux that we all know and love today, right? So Linux this is really, why am I talking about Unix? I mean, Linux really works almost exactly the same as Unix. And a lot of applications that are written to run on Unix also run on Linux. They're very similar. They're both written in C. They both support a lot of the same libraries. They have the same superstructure. You know, if you learned about the superstructure in other classes and some of the commands that you run, you know, pretty much most of the things that you do in a Unix-based operating system, those same commands generally work in a Linux-based operating system. They may not be the same code underlying those commands, but they're built to work the same way. And the standard that really helps that is POSIX, right? So POSIX is a standard that defines some common commands and what they should do. It doesn't tell you what, you know, who writes them or where the code came from, but it defines how they should work. So that's where we are in 1991, and then fast forward today, and Linux is one of the most common operating systems today. Probably second to Unix and then Microsoft Windows, right? And I say second to Microsoft Unix because if you look at this diagram, Mac is really a derivative of Unix, right? So I would say that Unix is probably the second most common. And when we look at things like Android, right? Android is really a derivative of Linux, right? So that would fall under that Linux heading. So one of the things we have to ask ourselves, you know, I was just talking about Microsoft and Xenix, and on that previous diagram, everything that was in pink was commercial software, right? So Unix is not an open source, inherently an open source platform. A lot of it is commercial, right? You know, Microsoft was in the Unix business. That was commercial. That was not open source. As well as Sun Microsystems with Solaris, and HP with HPUX, and IBM with AIX, Mac with their OS X, right? Those are all commercial operating systems, but Linux at its core is an open source operating system, so it's a little bit different, right? So what is the difference between open source and commercial, and why do we care about that in a network, in an operating system security course? So there's kind of a balance here, right, as to which one is better and which one is worse. And, you know, I don't really think one is really much better or worse than the other for a variety of reasons, but there's certainly pros and cons to both. And, you know, from the open source side, the big pro that most people point to is that it is free, right? And I put free in quotation marks because, you know, normally when people hear the term free, they think of free beer, right? I'm getting something for free, and free beer is probably a good thing, but that's not what we're talking about. It's really, we're talking about freedom, right? And which is better, right? Free beer or freedom? And when we say freedom, we mean you have the freedom to do whatever you like. Does that mean that it's free? Not necessarily, right? Companies that use open source operating systems or that rely on open source operating systems, they're still paying for it, right? They might be paying for support. They might be paying for a commercialized version of it, or a version where, you know, you're paying for certain components that are commercialized. There's nothing that says that you can't sell open source software, right? You can certainly sell it. You just have to disclose the code, right? The underlying source code has to be disclosed with open source, but that doesn't mean that you can't sell it. So there's certainly ways that it's monetized. So I hesitate to say that it's free. I even hesitate to say that it's cheaper. People have done a sort of, side-by-side comparison on whether it's cheaper to run Linux or Microsoft, which is obviously a heavily commercial operating system. And in some case studies, it comes out pretty even because you have to pay for support either way. And with Microsoft, some of that's included, and there's other things involved there, right? And some infrastructure provided by Microsoft. So it's kind of hard to say which one is really cheaper, right? So I don't want to say that it's free, but it is free as in freedom. So the next thing is transparency. Open source software, the source code is available for anyone to inspect it. So anybody can have the ability to go in and look at that source code. Now, some people will say, Brian, well, wait a minute. Doesn't that make it less secure because the attackers will know how it works? And the answer is, well, no, because yes, attackers can figure out how it works and attackers can get a good understanding of it works, but so can security professionals, so can computer scientists and the many, many people that look at that source code, which really brings me to the next point is power in numbers, right? Arguably with so many people that have access to the source code, it is very well written because there's so many eyes on it, right? There's so much scrutiny on it. You have all the best minds in the world that are able to look at the source code for these open source systems. So it really does give it a high quality level. Some people say, well, gosh, wouldn't the quality be better if you're hiring engineers to write it all in-house? And that's not always necessarily the case. Now, that's not to say that the code that's written for Linux is written by a bunch of people sitting in their basement doing it part-time, right? That's certainly the case for some of it, but you'd be surprised. Some people are surprised to learn that most of the source code for Linux is written by commercial companies, right? It's written by commercial entities that are commercializing portions of Linux, or maybe they're selling support and so forth. We'll talk about some of the different distributions, but the companies that are responsible for those distributions are paying developers to create some of that code. And why are they doing that? Because they want people to use it because they get paid to support it, right? So they're not copywriting the source code. Instead, they're monetizing the support and the implementation, and some of the proprietary tools that they can give you for that operating system. Now, on the other side of the spectrum, commercial, well, for all of the good things about commercial, there's some things that are not so good, right? So some downsides for commercial. One, one of the good things about commercial is they use the term one throat to choke, right? So that means, when you have open source software, it could have many different people have contributed to it. So when something goes wrong, who do you blame? Who's responsible, right? And it's not always clear with open source. Even a vendor that you're paying for support may tell you, well, we're not responsible for that particular component. Or, there could be a gaping security hole somewhere and they're going to absolve themselves by saying, well, we didn't create that utility, just go ahead and remove it, right? So, there's just so many people involved. But with commercial software, you have one vendor that you can call for all things related to that operating system, and Microsoft being probably the best example, right? Microsoft is this monolithic vendor that gives you everything you need with the operating system, all the utilities, and a lot of the different components we're going to talk about are all included under one roof with Microsoft Windows Server, right? So again, there's that concept of one place to go, one throat to choke, and that's certainly something to be said for that. There's also more accountability with the commercial vendors, right? If I'm paying Microsoft for my operating system, they are ultimately responsible and they take on some of that risk. That's why I use the term risk transference. I'm transferring some of that risk to Microsoft. And if Microsoft has some gaping vulnerability in their software, I can, as an IT administrator or even a CTO or a CIO, I can shift some of that responsibility to them. I can say, look, they were our vendor. They're the ones that screwed up, not us, right? Where that's much harder to do with Linux or Unix. There really is nobody to go after, right? There's no veil behind which you can hide when these things happen. And then the other thing that we have to talk about is transparency. We have a very high level of transparency in open source, but one of the bad things about commercial is we have very little transparency. Now, there are some companies that make commercial software that will put source code in escrow. And the reason that they'll do that is if I'm buying some very expensive software, for example, let's say I'm an airline and I am buying software that's going to run the entire airline. Well, that means that the company that wrote that code represents a significant risk to my business. If they go out of business, then I don't have a business, right? So companies that, very large companies that rely on much smaller companies' intellectual property to operate their business, they'll insist on source code and escrow. And the idea being that if that smaller company ever goes out of business, it disappears or whatever, they can take ownership of that source code and they can transfer it to another company and they can maintain that software. Most companies don't do that, but that's certainly an option. But that's the only way really that we have to get transparency. There's no obligation these commercial companies have to share that stuff. And I use the example of the man behind the curtain, right? In Wizard of Oz, they go to see the wizard and it looks all scary and the steam and all this big stuff happening, but in reality it's just some guy behind the curtain, right? And that's really what's happening. And with commercial software, we don't know what's behind the curtain, right? That's the concept here is pay attention or pay no attention to the man behind the curtain, right? So what exactly is the kernel in the sort of the core of the Linux operating system is really the kernel. When we use the term Linux, we're usually talking about this whole ecosystem, this whole computing environment built around Linux. But at its core, it's the kernel. So what does that mean? What's that look like? This is not an OS architecture course, but I'll give you some basic background here. At the core, you've got hardware. And the kernel is basically the software that can interact with that hardware. The kernel is basically your liaison to memory, processor, various hardware, and so forth, right? And a lot of these lines get blurred now with cloud computing, right? Which we're actually going to use in this class for our labs. But the kernel is really what's responsible for the hardware. And what's nice about that is everything you do around the kernel, like the shell, for example, everything's being translated through that kernel. So when you run the shell, your shell is running outside of that kernel, and when you issue a command, it's issued to the kernel, which then does things with hardware to carry out whatever it is you ask that command to do, right? So that's the basic concept here, and this is really the concept of abstraction, right? Which I used that term earlier in the course. So basically, hardware is abstracted from the software, like the shell, and the kernel is what's responsible for doing that. So the kernel is that layer of abstraction between the hardware and other software. Now in that layer just outside the kernel, you'll find things like the shell, various utilities, and then you have your processes, services, daemons, right? Things that run in the background, like your Apache web server, for example, or a DNS server. And then you also have runtime environments, which can handle things like Java, or the graphical user interface for your desktop environment, which run on yet another layer outside of that shell layer. So again, in the core, you've got the hardware, and then the kernel is what wraps around the hardware, and then around that you get your shell, and then within the shell you've got a runtime environment which could have things like Java or even .NET, right? So .NET works in Linux as well, right? We always think of Windows with .NET, but there's .NET Core which is available in Linux, right? So Microsoft technologies can run in Linux now. So which is kind of another interesting topic here is, and I'm sorry I have the wrong header on there. This isn't really kernel. We're talking about distributions here. So distributions are how these different versions of Linux are packaged, right? So the kernel, which we just talked about, which is the core of Linux, you've got this one kernel which is constantly being updated. Every so often a new version of the kernel is released. But it takes more than a kernel for the operating system, right? The operating system is not just the kernel. It's everything you saw in that previous slide. It's the shell, it's the utilities, it's services and daemons, and it's runtime environments, desktop environments, and so forth. And all of that stuff are packages that are part of the that are added on top of that kernel, right? So the kernel is in the middle, and then you have these packages that run, around the kernel, and for example, with the shell and utilities and so forth. So really, the two main distributions of Linux are Red Hat and Debian. Wikipedia would disagree with me on that, but my take is that those are the two main ones. Wikipedia's got this crazy chart you can look at, and they barely even talk about Red Hat on that chart, but I think Red Hat's a really important part of the distribution ecosystem in Linux. But anyway, you've got these two distributions. You've got Red Hat, you've got Debian, and really the main difference between those two, right? They both work very similar. A lot of the commands and the utilities are the same. Apache is really the same whether you run it on Red Hat or a Debian-based distro. But really what sets these two apart is the package manager, right? And really it's not just the package manager, but it's the packages that get packaged with that distribution, right? So what happens is some groups will take the Linux kernel and they'll curate a collection of packages to ship along with that kernel. So when you install that version or that distribution of Linux, it's that kernel with certain things that are curated to go along with that kernel that just kind of come with that distribution. Now, what that means is you could have a Red Hat distribution and a Debian distribution that have exactly the same stuff and work exactly the same way, right? Theoretically, you could do that. You could get a very bottom of the barrel basic version of Red Hat that has very little. And same thing with Debian, a very low level version of Debian. Then you could put the same packages on both and they'll both work almost the same way with a few minor differences based on how the package managers work. And that's the next thing is the kind of the main difference between these. What you really can't change easily, although you can, right? Is the package manager. By default, Red Hat comes with RPM, the Red Hat package manager, whereas Debian-based distros use the apt RPM package manager. Now, that's not to say if you have Red Hat, you can actually use RPM or the yum command, right? Yum is kind of the utility we use with RPM to install packages, and you'll see that in this course because we're going to use the Red Hat distribution of Linux. But you could technically use RPM to install apt-get and then use apt to manage your packages, right? And likewise, you could use apt-get in a Debian distro to install RPM and the yum utility to manage your packages with that if you prefer. But at that point, why wouldn't you just install Red Hat to begin with, right? Or a Red Hat-based distro. So really, it's the differences here are minor, right? They're not huge, but the important thing is it's the same kernel, has all the same utilities, the same applications run for the most part. The utilities and the configurations are very similar. There might be minor differences between these, again, mostly with the package managers and the packages that they come with. Another example is how you run services. The utilities for services and daemons are a little bit different in Red Hat than they are in Debian, but that doesn't mean that you can't go and install the package that makes them work the same way in either one of them. You can theoretically do that, right? So, but again, the package manager, that's the big thing that most people think about when they think about the difference between these two. Now, with Red Hat, there are distributions that are derivatives of Red Hat, right? So, for example, Red Hat makes this, has a distro, and it's got a whole bunch of packages and utilities that it comes with. And then somebody takes that Red Hat and they say, I want to make a slightly different version of that, and it's Fedora. And then somebody else says, I'm going to make a slightly different version of that, and it's CentOS or CentOS, depending on how you pronounce it. I'll call it one or the other, right? But that's, these are all derivatives. And likewise with Debian, same thing, right? You've got the two big derivatives of Debian are Ubuntu and Kali. Ubuntu is a pretty common Debian based distro. Both of these, and I should tell you that the Red Hat distros, Red Hat really comes from a company called Red Hat, right? So a company called Red Hat created Red Hat, right? It's their distribution of Linux that they commercialize. And likewise, Canonical commercializes Ubuntu and Debian, right? So this is really kind of how they're derived from each other. And again, different package managers. And even within these two, so, for this class, for example, Ubuntu, there's even derivatives of Ubuntu. So Ubuntu is a derivative of Debian, and then Xubuntu and Lubuntu, these are derivatives of Ubuntu. Xubuntu, for example, is a very basic distro that has no GUI, that is stripped down of most packages. So it's great for small implementations, right? And there's other distros that are great for that too. Arch Linux and things like that. Mint even has a very small distro. And again, those are all derivatives of either Red Hat or Debian. Kali Linux, which I have here on the right, most students in a class like this would say, Brian, why aren't we using Kali Linux? That is a security-based Linux distro. We're not going to use Kali in this class, and I'll tell you why. Kali is a Linux distro that comes with a lot of packages for doing network security testing, right? So it has a lot of utilities with doing things like intrusion detection, and it has utilities like Wireshark and, you know, port sniffers and all kinds of stuff like that, right? A lot of network security tools that, you know, somebody that's trying to assess a network might use. So we're not going to use Kali because the focus of this course is taking a commercial off the shelf or standard Linux distro and securing it and knowing how to administer it. We don't usually take Kali and use that to run our infrastructure, right? Kali is really kind of a toolbox of things we use to test things, right? It's not something we wouldn't really take a Kali distro of Linux and use it to build a web server, for example, right? It wouldn't be common to do that. So for that reason, we are going to mostly use CentOS in this class. I'm going to ask you to use CentOS. Could we have used Ubuntu? Sure. Could we have used Fedora? Absolutely, right? But our book talks a lot about CentOS. I think a lot of the commands that the book gives for examples are based around CentOS, so I thought it'd be easier just to stick with that. So we'll use CentOS in this class. And even CentOS has derivatives, right? Scientific Linux is based off CentOS. ROX Cluster, which is a cluster-aware distro of Linux. Oracle has their own distro of Linux, which is based off of CentOS, right? So Oracle took a derivative of that, right? Which is interesting because Oracle also owns Solaris, which is a Unix-based operating system. So as far as, you know, these different, you know, what's the pros and cons, you know, why would you use a distribution? Distributions are generally stable. All of these different components have already been curated and tested with each other. That we know they work well with each other. It's a lot more streamlined. You don't have to install a bunch of stuff. You can avoid unnecessary packages, of course, by building your own Linux if you want. But the problem with building your own Linux is, you know, if you do that, is that the dependencies aren't well managed, right? So that's handled by the package managers if you try to do it yourself. And then packages have to be compiled from source code if you're going to build your own Linux distro, right? So if you're going to build your own Linux distro, a lot of these packages you're going to have to build, and that's why a lot of them are derived, right? Red Hat did the hard work of doing a lot of that for you with their package manager. Same with Debian with the apt package manager. All right, so that's a little bit about distributions. Why are we learning about Linux? Why do we care about Linux, right? Windows is the cat's pajamas, right? Windows is a great operating system. It's really easy to use. It's easy to learn. Why do we got to get into this messy world of Linux, right? And the reality, and you know, some people will say, well, Brian, Windows is so much popular, so much more popular, right? Everybody has Windows. Well, that might be true on the desktop. That may be true when you walk in a classroom and you look around and all the computers on the desks have Windows. But when we look at operating systems in infrastructure, in the data center, in the cloud, that are really the horsepower behind the internet, behind the web, behind our modern infrastructure. Look at this chart. This is real. This is Linux makes up 96.3% of the 1 million most used web services are running Linux, right? Of those 1 million servers running the world's most popular web services, only 1.9% are running Windows and 1.8% are running Unix. So Unix actually has a smaller market share than even Windows, right? But Linux, as you can see here, is the lion's share. That's why when you looked at my timeline earlier and you saw all this stuff about Linux, and you're wondering, well, or Unix rather, and you're saying, well, gee, Linux is only this one little spot on the right-hand side of that chart. Look at all these other Unix-based operating systems. If I learned Unix, wouldn't I know a lot more operating systems? Well, I guess in theory you would have a more diverse understanding of some of these operating systems, but Linux is the one that's used the most. So it's where we're going to concentrate is on Linux. Now, could we learn Unix in this class? Sure, absolutely. In fact, I went to Camden County College a long time ago. Back in the 90s, I went to Camden County College, and we learned Unix back in the 1990s, right? Even though Linux had come out, it really wasn't as popular yet. You know, Solaris and AIX and HPUX were still all the rage in those days. We actually used AIX at Camden County College back in those days. It was around 1997, 1998. But today, Linux is what everybody's using, right? And look around you, not just, the world's most used web services, but pretty much everything, right? We talk about the Internet of Things, IoT. Look at your phones. All these Android phones are using a Linux derivative. A lot of the infrastructure that we use. Look at all these things in my picture I have here, like drones and robots and, like even manufacturing. Your smart TV, your thermostat, right? Your smart lighting, all this stuff. Even light bulbs you buy that are smart light bulbs that are Wi-Fi enabled. Most of those are running a really lightweight version of Linux, right? So you literally have Linux on light bulbs, right? So it's everywhere. We're seeing Linux on everything. So certainly not wasting our time learning about Linux. Now, some of the services that are typically provided by Linux, I keep talking about, Linux is so common. What kind of services are we going to see running on a Linux server? And really what we're trying to understand in Linux, what we need to understand is web services are running on Linux, like Apache and so forth. Apache, of course, being by and far and away the most popular web server. You have application servers that run in Linux that, for various applications. You've got file services running in Linux. Pretty much every major SAN or NAS that you see on the market. Look at NetApp and Dell EMC and these companies that are running storage for cloud and all that stuff. Under the hood, most of that stuff is running Linux file services like NFS and Samba for exposing data with SMB or UNC-Pass or CIFS, whatever you want to call it. Database servers, right? Oracle runs on Linux. Microsoft SQL Server now runs on Linux. It sounds almost sacrilege, right, for Microsoft to do that. But Microsoft, as of 2016 SQL Server, you can run it on Linux. They have a version of it that's built to run on Linux, and a lot of folks are moving to that, running it on Linux for a variety of reasons. In fact, I've heard that even Microsoft in their Azure cloud environment uses Linux for many of their services. So we see it there as well. Lots of other things that run. A lot of the common networking things that we use, like DNS, runs on Linux. Something like 95% of the world's DNS servers are running on Linux. And without DNS, there is no internet, right? DNS is core to the internet. Email services run on Linux. Now, that's not to say that you can't do all these in Windows, right? Windows servers can be a web server. They can be a file server. They can be an application server and a database server. But Linux, far and away, is much more common for these networked services than Microsoft Windows. With the exception of authentication, I would argue that in modern business, Microsoft Windows, what they do have the corner on is Active Directory services. So the idea of a network operating system that manages user accounts. Microsoft has a corner on that market for a variety of reasons, and they have an excellent product. I don't think really Linux has anything that competes with Microsoft's Active Directory services, or ADFS and all that stuff, right? Microsoft AD, and I say ADFS because with federated services, they can integrate with even third-party authentication mechanisms like SAML and OpenAuth and things that are usually Linux-based, right? In fact, Microsoft Active Directory supports LDAP, which allows it to be interoperable with Linux and other operating systems. When we talk about network security, any network security class you take, they're always going to talk about the CIA, not like the clandestine services of the Department of Defense, but as in confidentiality, integrity, and availability, like this triangle, which is the triad of the three things that the three concepts behind information security. And in plain English terms, availability is it's accessible when it's needed. You're protecting the information, that's confidentiality, and then accuracy and completeness, which would be under integrity, right? So that's really what we're talking about here. Some people argue that choose two, right? They say, you got three things here, choose two of them. And I would argue, of course, that we need all three of these, right? But what they're trying to say is that these, in some ways, these three can compete with one another, right? Availability is the big one, right? So availability, it's a balancing act of how much confidentiality you're going to have or sacrifice for availability, right? The more confidentiality you have, the less availability you're going to get to a point, right? So that's really what they're talking about, is this fine balancing act that we have to do. And something as IT security professionals that we have to constantly think about is, we don't want to ever do anything that's going to impact the availability of that data. It's really counterproductive. And I think far too many IT security professionals forget that. They're so concerned about, confidentiality and integrity that they forget about availability, which is what we're really here for, right? None of these information systems are useful to us if we can't get access to the data that's locked inside, right? All right, so some of the packages that are available in Linux that help us with security, that are used for network security, things like Bastion, Host, Snort, which is an intrusion detection system. You even have host-based intrusion detection systems like Tripwire and so forth. Syslog is the logging mechanism for Linux. It can consolidate logging across the entire network, which really helps with IDSs as well, but it also helps with troubleshooting and network security. IP tables is arguably the world's most common firewall, right? When you think about firewalls, most people think about Cisco, but Cisco probably has less than 50% of the world's market share in firewalls. The rest are other companies like F5 and Barracuda and so forth, some of the major vendors, and you have little ones like Linksys and so forth. But almost every firewall in the world that is not Cisco, right? Almost every firewall in the world that is not Cisco typically is running IP tables, the IP tables package. They might have other packages layered on top of that, but at their core, it's IP tables. So if you understand Linux and you understand IP tables, you probably understand the vast majority of firewalls out there in the world and in the market. So definitely important to understand it. NATing, there's packages that support NATing. Arguably, that's part of firewalls. Linux can include SSL and TLS for encryption, typically through open source libraries like OpenSSL, which can do both SSL and TLS. And again, those are really important for encryption and for data confidentiality. Some of the vulnerability, when we talk about vulnerabilities, so all this stuff I'm talking about, right? You've got all these different packages and these services that you can have in Linux. What really impacts network security and Linux security in general is as we add more functionality to Linux machines, they get more complex. And the more complex these systems are, the larger the attack surface, the more likely they are to be attacked. So it's an important concept, and that's why we usually talk about hardening. So probably one of the most important concepts in Linux security, which we're going to talk about periodically, is this idea of hardening, which is basically where we're limiting the number of packages and removing any critical user accounts. We're basically trying to strip down to the bare minimum. We're restricting permissions on files and directories, which we're going to learn about in this class, right? So a lot of what we're learning about in this course is hardening, system hardening, which really involves reducing the attack surface by limiting what people can access, limiting what's even there. If there's some issue with software, the best way to protect against it is for the software not to be there, right? Now, it's not always an option, so we have to mitigate that with other tools, which is where those security tools come into play, which I discussed earlier. So we'll remove unnecessary daemons and services and so forth. When we talk about the types of people that attack these systems, and again, every network security class and every cyber security class will talk about the concept of a black hat, a gray hat, and a white hat. And I don't want to spend a lot of time on it, but basically, when we use the term black hat, we're talking about the bad guys. When we use the term white hat, we're talking about the good guys. It's hopefully us that are learning about network security and cyber security. We're going to use those skills to help protect those systems, and then you kind of have this gray area in between. And your book kind of talks a little bit about why attackers are going after these systems. They're certainly not doing it for fun. There are, of course, some people that do, but for the most part, it's big money, right? Finding these vulnerabilities there's a lot of economic benefit to someone that can steal information. Either it's proprietary information from companies that they can sell to our adversaries like China and so forth, and maybe even Russia. And then it's also, selling things on the dark web like credit card numbers and stuff like that, right? So there's a lot of valuable information. In fact, I read one time, I work in the healthcare industry, and I was surprised to read one time that in the dark web, the most valuable information is healthcare data. and I think it has a lot to do with healthcare exposes a lot of very personal details about people, and that can be used to gain access to a lot of accounts and things like that. There's a lot of things that people can do with that type of private data. So sometimes it's surprising where they find value in some of that data. But that's really why these systems are attacked. I think it's good to be cognizant of that and be aware of that as we think about ways to secure these systems and why we're securing these systems. All right, so that concludes the content for our introduction. I also have a lab for you this week. So in the lab this week, it's going to be very straightforward. I have a video that walks you through it, but basically I'm going to ask you to sign up for a Google Cloud account. So really the deliverable for this lab is that you sign up for a Google Cloud account. I give you the information in the video. You're going to go to cloud.google.com. You're going to sign up for your account. I talk about this in the video, but you'll have to give them a credit card, but don't worry, they're not going to charge you. You're not going to need to pay for it most likely in this class, and even if you do, it won't cost very much. I think my virtual machines cost me about $4 a month to run, which is pretty cheap when you look at how much a textbook costs, right? So once you set up your Google Cloud account, you're going to install CentOS on a virtual machine in Google Cloud, or what they call a VM instance, right? So you're going to go into Google Compute Engine, and in the Compute Engine, you're going to build a VM. Why are we doing that? Because basically, we're going to use Google Cloud. Instead of building virtual machines on our own computers at home, I'm going to ask you to do it in the cloud. Why am I asking you to do that? Because I don't know anything about your computer at home. You could have a Mac, you could have Windows, you could have all different versions of Windows. Some of you are going to have old laptops that can't run certain things. Certain operating systems can't run with certain hardware, all kinds of variables. We can control some of those variables in the classroom, but I can't control them when you're at home. I don't want to waste a lot of time trying to get things to work on your computers at home. If you want to install Linux on a computer at home, by all means, go ahead and do so. But the cloud is a great option because, somebody like Google, there's also Azure and AWS or other big cloud providers, but they basically let you install install virtual machines on their computers in their cloud. And yes, you have to pay for it, but it's incredibly inexpensive. And in fact, Google gives you 300 credits to use for the first 180 days. So for a half a year, you've got 300 hours to spend. And I can tell you that if you build the machine I tell you in the video, it will cost you about $4 a month to run that machine. And even if you forget to turn it off, it'll cost you about $4. Now, if you screw up and you create a machine that is super powerful, you might go in there and say, oh, I can build a machine with 64 processors and 22 gigabytes of RAM. Yeah, that's going to cost you a lot of money to run that machine, right? So I'd advise you not to do that. Follow my instructions and build a very basic machine. It's all you're going to need for this class. We don't even need the desktop. We just need a very basic CentOS 7 system running in the cloud. It's a quarter of a processor. It's less than a gig of RAM. That's all we need. And that's one of the things that's nice about Linux is you really don't need a lot of resources to run Linux. It'll run pretty well without the desktop environment. It runs pretty well on almost anything, even a light bulb, right? So we're going to install a CentOS instance, and then basically you're going to configure it so that you can access it with SSH. SSH is a protocol. We're going to learn about it in this class, but it's basically a way to get an encrypted login to your server remotely. Even if you installed your machine on your own computer, you would still want to use SSH to access it with PuTTY or something like that, or PowerShell. What I like to use in this course is if you're running Microsoft Windows, you'll have something called the PowerShell. PowerShell includes a native SSH client that you can use to connect to your Linux machine in the cloud. And if you're running a Mac, it can also support the SSH command, and it works exactly the same way. I don't know how to get to the command line in Mac, so please don't ask me, but if you do, I'll Google it for you. Or you can just Google it yourself, how to do it in a Mac. I don't have a Mac, so I very rarely use it. But if you have a PC, very easy. Look at my video. It'll show you how to do it. What I'm going to ask you to do is send me a screenshot. In the video, I show you where I want you to take a screenshot to show me that you have your VM built and that it's working. And you're going to see how easy this is. It is so easy to set up a machine in the cloud. It's a lot easier than installing our own VMs from an image and so forth. It goes very smoothly. So I'm pretty comfortable with us moving in that direction. So if you have any questions, please let me know. And thank you for watching, and have a great week.